Welcome, guys. In this video, we are going to continue our topic on analysis of functions. Today, we are going to learn how to draw rational functions and more general functions. We'll also touch on topic of cusps and vertical tangency cases. So let's start by drawing rational functions. Let's recall that rational function is a function of the form p of x over q of x, where p and q are polynomials and have no common factors. The first step, we are going to study symmetries, if there are any symmetries about y-axis. To find whether our function is symmetric about y-axis, we need to substitute minus x instead of x into our function, and if it is the same as f of x, then our function is symmetric about y-axis. Next step is that we are going to find x and y-intercepts. Then we are going to find vertical asymptotes. These are zeros of denominator for rational functions. Then we are going to find the intervals where our function is positive and negative. In step 5, we are going to find horizontal asymptotes and study end behavior of our function. Then we are going to find first and second derivatives and study intervals where our function is increasing, decreasing, where our function is concave up, concave down. We are going to find relative extrema points and inflection points. And finally, in step 7, we are going to gather information from all of these steps and finally draw our function. All right, so let's get straight to the point. Let's plot the following rational function. Let's express it as, let's factor out 2. So we'll have x minus 2, x plus 2 in numerator, and x minus 4, x plus 4. So indeed, these two polynomials have no common factors. They cannot be further simplified. First step, let's find symmetry. Symmetry about y-axis. Okay, so if I substitute value of minus x, we can see that both x squared and we have also x squared in denominator, so both of these have even power, so f at minus x is going to be equal to f at x. So our function is symmetric about y-axis. There is a possibility that in some other rational functions or some other functions, you might see symmetry is about other vertical line other than y-axis. Okay. So we'll study some cases further on. Now, let's find x and y-intercepts. So let's start by finding x-intercepts. To find x-intercepts, we need to solve equation f of x is equal to 0. So if we set that to be equal to 0, then the solutions are in our numerator, x is equal to minus 2 and x is equal to 2. So these are our x-intercepts. Now let's find y-intercepts. So to find y-intercepts, we need to find the value of function at 0. So we'll have only, of course, we'll have only one y-intercept. Otherwise, our function will fail vertical line test and it's not a valid function. So if we substitute 0 to our function, then we have minus 8 over minus 16. So this is equal to 0.5. So here is our x-intercept, and these are our these are x-intercepts, and this is our y-intercept. Okay, next step is that we are going to find intervals where our we are going to find vertical asymptotes. So vertical asymptotes. Let's copy this down here. Vertical asymptotes are zeros of denominator for rational functions. So x minus 4 and x is equal to 4. So these are our vertical asymptotes. Okay, our next step, we are going to find intervals where our function is positive, negative. So let's copy this down again. So this is our f of x. Now let's draw the real line. Let's indicate zeros of numerator and denominator. So these are minus 4, minus 2, 2, and plus 4. So all these roots have odd multiplicity, so the sign over these points will alternate. If we substitute plus infinity, this is positive, positive, positive. So on the interval from 4 to plus infinity, our function is positive, then negative, positive, negative, and positive. So these are for sign of f. Okay, our next step is that we are going to find study and behavior of our function. Let's find horizontal asymptotes. So let me copy our function. Okay, if we take limit as x goes to plus infinity of our function f of x, then this is equal to 2. As a ratio of two polynomials, we look only at the highest power terms. Then limit as x goes to minus infinity of our function is equal to also 2 when x goes to minus infinity. So x is equal to 2. Y is equal to 2 is our horizontal asymptote, the single horizontal asymptote for both cases when x goes to plus and minus infinity. So this is for end behavior. All right, now let's find derivatives. I already copied this down to keep doing some algebra. So first derivatives are given here, second derivatives are here. Now let's find intervals where our function is increasing, decreasing. To do so, we are going to draw a real line, and then we are going to study the signs of f prime. So for f prime, we have x is equal to 0. Critical points are x is equal to 0, which is stationary point. So let's write this down. This is stationary point. And we also have a couple of critical points at x minus 4 and x plus 4. So minus 4 and plus 4. These are critical points where our function is not differentiable. Then this has odd multiplicity, and these two have even multiplicity, as we can see here. So sign over this will not change, and sign over 0 is going to change. Let's substitute plus infinity here. This is positive, this is positive, so our function sign of f prime is negative here. Over this even multiplicity, the sign of f prime is going to change. Then here our sign is going to change, since this has even multiplicity, then sign over minus 4 isn't going to change. So our function is increasing, increasing, then decreasing and decreasing. So we have one relative extrema at a point x is equal to 0. Here we have a relative maximum. Since our function is increasing, then decreasing. Okay, so that would be it for studying the signs of f prime. Now let's study signs of f double prime. Now we are going to draw a real line. We are going to indicate points where second derivative is equal to 0. So these are no zeros in numerator, and x is equal to -4 and 4. So these are zeros of denominator. Now let's find, so both of these have odd multiplicity, as we can see here. This is cubic root of that. Now let's substitute plus infinity. This is positive, this is positive. So plus, meaning that our function is concave up. Odd multiplicity, both of this, so the sign over this will alternate. Concave down on interval from -4 to 4, then it's concave up on interval from -infinity to -4. Okay, now let's finally let's gather all this information up, and let's finally make a sketch. All right, so we know that our function is symmetric about y-axis. X-intercepts are -2 and 2, and y-intercept is at 0.5. So x-intercepts are at -2 and at 2. At 0.5, we have y-intercept. Then we also know that our function has vertical asymptotes at -4 and 4. -4. And at 4, we have vertical asymptotes. Okay. Next, we know that our function is positive on interval from -infinity to 4. So our function will be somewhere here, then it will alternate. Okay, then we also know that our function has horizontal asymptote at y is equal to 2. So horizontal asymptote somewhere here. Okay. Then we know that our function is increasing on interval from -infinity to -4. So increasing here. Then it keeps increasing on interval from -4 to 0. Then it is decreasing afterwards. We also know that our function is concave up to -4. Then it's concave down on interval from -4 to 4. And then it's concave up on interval from 4 to +infinity. All right, so we are ready to make a sketch. So our function has horizontal asymptote here. It's negative there. Then it is increasing, and also we know that it's concave down. So it will look something like that. Okay, now on interval from -infinity to -4, it's concave up, it's positive, and it has horizontal asymptote at y is equal to 2. All right, so our function will look something like that. So we should keep in mind that it has also vertical asymptote at point x is equal to -4. So these blue are asymptotes. Okay, we also know that our function is symmetric about y-axis, so we are done here. All we need to do is to reflect it about y-axis. Okay, so our function looks something like that, so in black. let's check. So it's concave up, it's decreasing. Here it's also decreasing, concave down, positive. So it is positive. It should be positive on interval from to -2 to 2, from -2 to 2. Okay, so that's okay. Let's erase this asymptotes to see more clearly what's happening. All right, so here's our graph then. In rational functions, if the degree of numerator does not exceed the degree of denominator, then the asymptotes that we have seen so far were only either vertical lines or horizontal lines. In the cases when the polynomial has higher degree in numerator than denominator for rational functions, then some other cases might arise. These are known as oblique or slant asymptotes. Let's take a look at the following two cases. If we further by division rewrite them in the following forms. So here we can factor out x squared, we'll have x minus 1 minus 8 over x minus 1. So we can present this as x squared minus 8 over x minus 1. Then in these cases, as x goes to plus or minus infinity, our function is going to oblique to non-vertical or horizontal line. So if we look at the plot of this rational function, we see that as limit goes to infinity, we have this x term appearing in front, and our function will try to reach up to this line y is equal to x. And in this case, we can see that as limit goes to infinity, so that term will disappear and our function will try to reach up to this parabola x squared. So like we see in this plot here. And in that case, we also have a vertical asymptote at x is equal to 1. Okay, so here this is a nice plot for this rational function. So in general case, if the highest power term in numerator exceeds the highest power term in denominator, then we can present our rational function in the following form, and q of x is going to be oblique or slant asymptote when x goes to infinity. All right, now let's study the cases when we have graphs with vertical tangent lines and cusps. So vertical tangent line appears in the case when the slopes of tangent lines when we approach some point x0 are going to go to plus infinity and from left, and plus infinity when we're approaching from right. So in this case, if you look at slopes of tangent lines, you can see that they are going to go to plus infinity when we are approaching x0 from right and when we are approaching 0 from left. So in this case, we have a vertical tangency case as follows. In case when both of these limits go to minus infinity, then we have vertical tangency like that. In case when the signs of derivatives differ, limits of derivatives differ when we approach some point, then we'll have a case of cusp. So these two are examples of cusps. Here, both slopes go to, this slope here goes to plus infinity when you're approaching from the left to point x0, and this slope here goes to minus infinity when we approach x0 from right. Okay, so if the values of this infinite limits differ, the signs of this infinite limits differ, then we have a case of cusp. And here another example of cusp. So this is plus infinity when we approach from the right, and minus infinity when we approach from the left. Okay. All right, so we'll see these cases when we'll plot some additional graphs. All right, let's sketch the graph of the following function. It's not a rational function, but we can use the steps that we applied for rational functions. So then let's start by finding any symmetries. There is no symmetry about y-axis, but we have a symmetry about x is equal to 4, as we can see from here. If we, for instance, use substitution x minus 4, then y can be represented as t to the power of 2 over 3. This graph is symmetric about t is equal to 0, since here we can see t to the power of, so we can represent this as cubic root of t squared, and this is symmetric about t is equal to 0, and when t is equal to 0, x is going to be equal to 4. So our graph is symmetric about vertical line x is equal to 4. Let's find x and y-intercepts. Okay, x-intercepts are, so there is only a single x-intercept at x is equal to 4, solution of y is equal to 0. Now, if we substitute x is equal to 0, we get minus 4 to the power 2 over 3. So this is cubic root of 16, which is approximately 2.5. Now, next step, let's find vertical asymptotes. So as we can see here, there are no vertical asymptotes. All right, so since there is nothing appearing in the denominator, and we can see that our graph is continuous on interval from minus infinity to plus infinity. Let's find any horizontal asymptotes. Let's study end behavior. When x goes to, we'll use that in a second. When x goes to plus infinity, the limit when x goes to plus infinity, that goes to plus infinity. And when x goes to minus infinity, since we can consider this as even multiplicity, that limit will also go to plus infinity. All right. Now let's find derivatives. So derivatives are already found here. To skip some algebra. Now let's study, oh, I forgot a step. Let's find intervals where our function is positive and negative. To do that, so this step is for sines of f of x. To do that, we are going to draw a real line. We will find the roots of f of x is equal to 0, a single root at 4. Now, if you substitute plus, so that root, we can consider this root having even multiplicity. Now, if you substitute plus infinity, this is plus, this is plus. So our function is positive everywhere. Now, let's study the sines of f prime. So as we can see here, we have a single critical point at x is equal to 4. Now, if we substitute plus infinity, which has, we can consider this having odd multiplicity. If we substitute plus infinity, this is plus, minus. So our function is decreasing, then increasing. At 0.4, then we have relative minimum. Okay, now let's, also we can see that now here we can see that at point x is equal to 4, we have a critical point. And let's take a look at limit as x is approaching to 4 from left side of f prime of x. So this limit, if you substitute some value that is smaller than 4, that will be a negative 0. So this is minus infinity. limit as x goes to 4 plus. So when we approach to 4 from the right side, that will be a small positive number. The limit of f prime when x is approaching to 4 from right side, that will be plus infinity. So as we can see here at point 4, we have vertical tangency case, and our slopes decrease infinitely, and then they increase infinitely when we approach from the right. So we'll have a case like that at point 4. So vertical tangency at point 4. Now let's find inflection points, and let's study signs of f double prime. So single root at 4, we can consider this root having an odd multiplicity, even multiplicity, so the sign over it will not change. If we substitute plus infinity, our function is concave down and concave down. All right. And at point 4, we have inflection point. Okay, now let's make a sketch. 1 second, let me add the axis. Okay, so let's gather our data. We know that our function has y-intercept at y is equal to 2.5. At 2.5. Then a single x-intercept at x is equal to 4. Okay, no vertical asymptotes, no horizontal asymptotes. Our function increases without bound when x goes to plus and minus infinity. All we need to do, since we know that our graph is symmetric about x is equal to 4, to draw everything up to 4 or after 4 and then make a reflection. Then we know that our function has a relative minimum at 4. It's positive everywhere, and it is decreasing up to 0.4, and it is concave down. Okay, so then our graph will look something. Let me change it a little bit. So our function will look something like, so it's concave down. At 0.4, we have vertical tangency case like that. And then we'll make a reflection. So something like that. So our function is decreasing, it's concave down, and we have vertical tangency at 0.4. So that is graph of our function provided here. All right, so let's now sketch the graph of the following exponential function. Again, this is not rational, but we can use the same steps. First, let's find symmetries. We can see that it's symmetric about 0, about our y-axis. Then let's find x and y intercepts. So x-intercepts are, there are no x-intercepts since no solution for f of x is equal to 0. Let's find y-intercepts. If we substitute 0, y is equal to e to the power of 0, so this is 1. Now let's find vertical asymptotes. There are no vertical asymptotes. since our function is continuous everywhere, as we can see here, so there is no value such that our function is not defined at some x. Then let's find horizontal asymptotes and study end behavior. So limit when x goes to plus infinity of f of x. If we substitute plus infinity here, that will be e to the power of 0. That will be e to the power of minus infinity. So that will be 0. And when we find limit when x goes to minus infinity, f of x, we have the same situation, e to the power of minus infinity. So this is 0. Okay, now let's find derivatives. We already found derivatives here. So first, again, I forgot to study the signs of sign of f of x. We can see that our function is positive everywhere. Now let's find intervals where our function is decreasing, increasing, concave up and concave down. So first, let's study the signs of f prime. So a single critical point at x is equal to 0, which is also a stationary point. So this is always positive, meaning that if we substitute plus infinity, that will have negative sign, and it will alternate over x is equal to 0. So our function is increasing and then decreasing. At point 0, we have relative maximum. Now let's study signs of f double prime. So points where f double prime is equal to 0 are -1 and 1. So this is always positive. When x goes to plus infinity, this is plus, minus, plus. The sign will alternate. So our function is concave down, concave up, concave up. So we have two inflection points at -1 and 1. Right, so I have my axis here. Now let's finally make a sketch. We have y-intercept at y is equal to 1. We also have relative maximum at that point. Our graph is symmetric about y-axis, so all we have to do is sketch one part up to 0 or after 0. We know that our function has horizontal asymptote at y is equal to 0. Okay. We also know that our function is increasing up to point 0. It's concave up to point -1, up to point -1, and then it's concave down. Okay, so let's make a sketch. So it's concave up, increasing, still increasing, but concavity is going to change at point 1. At point x is equal to -1, so it will become concave down. All right. Then we can reflect it about y-axis. And here is our second concavity point at inflection point at x is equal to 1. All right, so here is a plot of our graph.